All right, so we're going to start Unit 3 now on model order selection and the bias-variance trade-off. So here we're going to get into some real kind of machine learning concepts. So just to continue from something that was motivated in the last unit, polynomial regression. So in this case, the model that we have is that y is approximately equal to beta naught plus beta 1x plus beta 2x squared, and so on, all the way up to beta d x to the power d. So as we saw, the model parameters, just like in standard linear regression, multiple linear regression, are beta 0 through beta d. D is the degree of the polynomial. That's just what it's called. And if we decide what d is, then we can fit beta using least squares, just as we described using this simple approach right here. So the whole question now, though, is how do we choose d? Can we select d from the data itself? This is important because in machine learning, we don't want to have to go to a domain expert and have them tell us about the physics of the problem. We want to just be able to look at the data itself and figure out how to do the modeling from the data alone. In this problem, we call model order selection because it's like trying to decide the complexity of the model. The more of these coefficients we use, the more complex our model gets. And as we'll see, there's a cost to the model becoming too complex. So in this case, if I create data where I'm told exactly the true model, as you can see, I can do a pretty good job of fitting the data. So let's see how we generate this data. This is what's done in the demo for this unit. And in this case, there's no data set we're loading. We're just going to create our own data. It's going to be synthetic data. And the reason we're doing that is synthetic data is really useful if you want to experiment with something, prototype something, because you know the truth. Because you created the data, you know the truth. You can say exactly what the error is, what is correct, what is incorrect. So that's what we're going to do in this case. We're going to use synthetic data. And in particular, we're going to generate our data from a noisy polynomial model. So in terms of our features, so our features x are going to be randomly chosen on the interval between 1 and -1. And they're uniformly distributed over that interval. So we're just going to, let's see. So here you can see it. It's the numpy.random.uniform, and you tell it the boundaries -1 to 1, and you tell it how many samples you want it to generate, and we're going to store those in this xdat vector. Okay, now what about the y's? So what we're going to do is we're going to generate them as some polynomial, so yi is some polynomial function of xi plus some random noise epsilon I. So here's the polynomial function. This is the true polynomial. So these are the true coefficients, beta 0 plus beta 1x, all the way up to beta d times x to the power d. And in this case, the true model has an order of 3. And the noise is going to be Gaussian. So this script n for us is always going to mean Gaussian or normal distributed with mean 0 and variance sigma squared. So this is the standard abbreviation for a Gaussian with mean variance. You just write the two things after the script n. And we're going to assume that the noise is statistically independent from one sample to the next. So that is exactly how we got these dots. So the horizontal thing was generated randomly. Given that randomly generated x, you can evaluate the polynomial, which tells you exactly where it would be on this red line, and then you add the noise, and that is what is putting these blue dots off the red line. But as you can see, it's zero mean noise in that the blue dots have an equal probability of being above or below the red curve. Okay. And as you can see, in order to do these polynomial manipulations, there's a nice library. It's this NumPy polynomial library, so we're going to use that. And polyval that evaluates a polynomial given these x samples and these coefficients beta. It gives you the corresponding y samples. And here we're adding the random normal or Gaussian noise, mean zero, standard deviation, WSTD, which turns out to be 0.2, and however many samples you want. Okay. So that's the data set we'll be using. Any questions on anything here? Yeah?
Where is pointing to the sigma squared?
That's the variance.
Oh.
Sorry about that. Variance and mean. Okay, so if somebody tells us the true model order, let's imagine they do, we can use, there's a couple approaches we could use to fit the coefficients. In the last unit, we learned about using the sklearn routine linear model.linear regression. We could do that. We can also use the NumPy polynomial package even to do the least squares fit as well. And this is done in this polyfit. Here. So this does the least squares fit. You would get the same result if you used the linear regression package from sklearn. It's just a little bit more convenient because we don't have to make the feature matrix and the so on. It's a little bit of a shortcut. So when we do this, we compute the least squares betas, and using those betas, we can generate another curve, which is the green curve here. And you can see that it's a pretty good fit to the true curve, right? The least squares betas give you a new polynomial, which is very close to the true polynomial. And that's, as we'll see, this is in part because we knew the right order to use. If we know the order, least squares works well. Now, if we don't know the order, it may not work well at all. So here's one example. What if I use order 1? As we know, that corresponds to fitting with a line. As you can see, that line is quite different from the true polynomial curve, right? So this is what we call underfitting. Now, we could also try to use a model order that's actually significantly higher than what we know to be true. And in this case, you get this green curve. The green curve does a decent job here, but then you can see something weird happens towards the end. And this is just one example. Let me show you some other pictures of what happens. I almost like these better. So this would be, so here you can see the data. The true model might be something like this. This is clearly underfitted, and this is an example of what can happen if you overfit. So here you have a model that's so complex that it can go perfectly through all your points. Okay? But the thing is, what you're actually modeling at that point is the noise, not just the data. Because what's really causing all those wiggles is the noise you added. The actual model underlying this is smooth. The smooth thing is what we'd like to measure. And the reason why is if if someone gives me a new sample that I had not seen at test time, for example, that new sample might be over here. And now you can see how it's going to be very far from my model. Whereas if I had given a smooth model and my sample is over here, now it's actually much, much closer. My error is smaller. So this is a very important concept in machine learning, the concept of underfitting and overfitting. So underfitting, your model is too weak. It's not complex enough to really do a good job of fitting the complexities in data. And overfitting was your model is too complex and it starts to model random noise effects and things like that that are in your training data that will not be present when you apply this model later to what we call test data or new data, something like that. So now that you see that there's a cost to using too simple of a model or to using too complex of a model, the question remains, is there a way to estimate the true model from the data? How do we do that? That's what we would like to do. Any questions on underfitting and overfitting? Okay. So let's try a simple idea. What if I do this? I create a for loop, and in my for loop, for each hypothesized model order D, so I start with D equals 1, D equals 2, D equals 3, and so on, I compute the least squares coefficients for that model order, so there's always going to be D plus 1 of them. And then using those coefficients beta, I predict the targets in my training data, and I compute the RSS on those targets. And if I do this for all the different Ds, and I look at which D minimizes the RSS, do you think this is going to work? Here's an example of what happens when we do this on our data set. So as we're changing the model order D, going from small to big, my training RSS starts high. This is, when D is 1, I'm just using a single variable, a linear model, quadratic model, cubic model, quartic model, and so on. My model is getting more and more complex. My training RSS is just getting better and better and better. So if I use this approach, I will always choose the last D that I used. That's always going to give me the lowest error.
It will lead to overfitting.
Exactly. Exactly, and as we know, we saw in this example that using 14 when the truth is 3 is probably not a good idea. It's not going to give as good a model as D. We happen to know that in this case 3 is the right thing. And you can see on the training data, we can actually get much lower error. And so what's going on is kind of like something like this. It's possible in polynomial regression to finally find a polynomial that goes through all your points perfectly, at which point you will have 0 training error, right? But that does not mean that when you apply this model to new data later, you will have 0. You actually will have a lot of error. So that's the problem, is that training error alone is not enough to tell us this. So this simple idea does not work. As we see, the RSS monotonically decreases, or at least it never, we will eventually hit a point where it's 0, and then it never increases after that. So this suggests to choose D as large as possible, which leads to overfitting. So let's see if we can understand a little bit more about what's happening here. So let's think about a sequence of models that we have created in this experiment. So first, we started with a model when D equals 1. So if you think about the beta vector that we're fitting, it has 2 possibly non-zero parameters, and then all the others are effectively 0 in the sense that we are never using those features, never using the cubic, quartic, and so on. Now, when I increase D from 1 to 2, I get a new model where I have the same coefficients as before, but now I add an extra coefficient. And if I think about optimizing these coefficients on the training data, then this model will always do at least as well as this, and possibly even better, because it has more flexibility. It has the possibility to choose a non-zero beta 2. And so if that's the right thing to do, this new model will do better than the old one on the training data. And so on. If I move my model order up by one more, then I'm adding one more coefficient. And I now have a model that's even more general, even more capable than my previous one. So every time I do this, I get a model that's better and better and better, at least for predicting the training quantities. So the training RSS gets no worse as the model becomes more general. So this is try to explain a little bit about why it fails. Here's another illustration where we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points, and we have a model, a polynomial model that you can see perfectly goes through the points, the data points. In this case, the actual true model was linear, and the data points are just deviating from the linearity because of noise. So it's possible to fit that training perfectly, but it's not what we actually want to do. So that's what's happening here. We're trying to fit the noise when D is too large. That's another explanation for overfitting. Okay, so is the overfitting idea pretty clear? Okay. So this is a good time to stop. We'll next talk about how we deal with the situation. It's through something called cross-validation, and we'll save that for Monday. So wish you guys a great weekend, and we'll see you on Monday.